Well, happy week 9, everybody, and happy Monday. Thank you guys for coming to class. You guys have been it's like you, I appreciate you guys coming. And for those of you watching on YouTube, sorry you couldn't join us, but thank you also for watching. Um, you know, all right. Well, I thought we would just cover a little bit more stuff from sklearn. I wanted to talk a little bit about kind of cross-validation, train test split. These are going to be kind of some of the, this is the primary way that we check to see if the model, quote, works, the model performance works in machine learning. Whereas and this is in contrast to kind of classical statistics. So in classical statistics, when you evaluate a linear regression model, you check to make sure that your linear regression assumptions are reasonable. You want to check for things like, are the residuals normally distributed and things like that, right? And you'll kind of do, if you want to compare two models, you might do like a likelihood ratio test or something like that. And that's all covered in Stats 101A. So if you've taken that, hopefully those terms sound familiar. And if you haven't taken 101A, you will learn about kind of these classical approaches to check to see if your model is any good. And there's classical approaches for comparing one model to another. In machine learning, some of the models are so kind of weird and complicated, and we're kind of unsure about exactly what assumptions we're making when we fit a model. And again, some of the models have such, are so opaque and kind of trying to understand what's actually happening inside the model. So for example, if you were fitting a neural network, what exactly is happening inside of a neural network, it's very difficult to actually know. And so the way we would evaluate model performance is through cross-validation and using a split in the data and using kind of a holdout set or a test set. And so scikit-learn comes with a bunch of kind of tools and functions that facilitate that. And so today, I'm still going to just kind of fit linear models today, but I'll show you kind of how to go about using the tools for doing train test split and things of that nature. Okay, so first I'm going to go ahead and load up. Actually, we don't actually need the iris data for today. I'm going to load up a lot of our packages: NumPy, Pandas, PLT. And then we're going to take a look at a few things. We're going to look at linear model pre-processing, and we're going to import model selection. And from model selection, we'll also import train test split and cross-validation score. And actually, we are not going to use the neighbors or the naive Gaussian base. We're just going to do linear models today. Okay, so I'm going to go ahead and load that up. And this is kind of a little diagram of how, splitting the data between kind of training sets and test sets and validation sets kind of work. Okay, so a lot of times, you want to kind of figure out the best model to use, right? And so you might consider, should I fit a linear model? Should I fit a quadratic model? Should I fit a cubic model or something like that to the data? Should I do a log transformation? You have a bunch of options, right? And kind of in the classical, well, not even in the classical approach, generally the rule of thumb is the more complicated you make your model, you're going to get a better kind of R-squared score. You're going to get a better, you'll reduce your mean squares, residuals, and things like that. Okay, but is complicated always better? And the answer is usually no. A lot of times you end up overfitting the data. You end up with a really complicated model. You end up modeling or fitting some kind of feature that exists only in your specific data set and is not something that generalizes to the regular population. And so to kind of correct this from happening, you often will split your data between a training set and a test set, okay? And so what we'll do this, and the idea of the test set, which sometimes called the holdout sample, is that this is going to act as brand new data that we haven't observed, okay? And with the test set, you have your input values and you also have the answers. And what we're going to do is we're going to use the training data to figure out what model parameters, what slope, what intercepts to use. And we're going to say, okay, if I use that slope and intercept, how does this fitted line work on this test data? And you get kind of an estimate of how this might perform in the future when you see brand new data that you haven't seen before, because the test data is often like that. Is the idea that there's brand new data that we haven't seen. Okay. All right. And so what we've and then beyond that, we also have training. We're going to do cross-validation. Okay. And the idea behind cross-validation is that once you kind of split this holdout sample, you also kind of want to be able to take your training data, and as you're training your model and trying to pick models from there, you want to do kind of the same thing, and you want to kind of fit a model and see how well it performs on brand new data that it hasn't seen. But we're going to kind of repeat the process here with a validation set. Okay. And so again, the idea is we're going to split the data between training and test, and then we're going to fit it only on the training data. You're going to use the training data to kind of help figure out your model parameters. And then once you have your model figured out, you're going to test its performance on brand new data that you haven't seen before. Okay. And so kind of one of the first tools that we have is Traintestsplit. Okay. And so to kind of just illustrate how Traintestsplit is going to work, I'm going to create just a couple arrays here. Okay. I've got an array X and an array Y. Okay. And I also have this array Z that will come in later. Okay. But for now, X just is going to be kind of this 10 observations in 2 columns. Okay. And then Y will be a vector of basically 10 observations. Okay. And right now these are all just, the data is very simple. Okay. Just basically these 10 observations for X goes 0 through 9, 10 through 19, and then the observations for Y goes 0 through 9. But this is just mostly so you can see how the Traintestsplit will work. Okay. So Traintestsplit, and the way you're going to get that is from sklearn model selection, Traintestsplit. You're going to feed it in some input matrix X. You're going to tell it what proportion of the data you want it to put into a holdout set. Okay. And then you can use random state equal to some number. All right. And this is kind of like your set seed, so that if you want to reproduce your results, you'll get the same results again. Okay. And so what this will do is it will go through our X matrix, and it will, I have 10 observations here. So it's going to kind of put a quarter of them, and that's probably going to get rounded up to 3. So, 1/4 out of 10 observations is going to put a quarter of them into our test set. Okay. So here, X train and X test will get split into kind of two arrays here. Okay. It puts into the training set, we get 4031785. And then into the test, we get observations 296. Okay, and so it just kind of randomly goes over all of these and puts some into X train and some into X test. Okay, we can take, using the same random state, we can say, split Y. Okay, and it's going to split the corresponding Y into the training observations for Y and the training test observations for Y. Okay. And so again, when you give it some proportion, that doesn't exactly fit, right? So here I have 10 observations and I say I want 1/4 of them. 1/4 of 10 is 2.5. sklearn is going to kind of just round off to some number and try to do its best here. Okay, and so here with y, we can see, for the training observations, it pulls out the corresponding training values for y, right? So 403, 1785, and it pulls out those exact values, 403, 1785. And so the idea here is when you have a full data set, right, you've got all of your x values and all of your y values, it's going to do the appropriate splits, and it's going to split the x together and the y and the y's, and you'll have kind of your training data, and then later on for the test data, you'll have the test observations. Okay, you can actually do x and y simultaneously, so you can just say and so what this will do is it'll produce a tuple of length 4. And so if you do x, train test split on x and y, it's going to create x train, x test, y train, y test. And so I'll go ahead and I'll split all of this out. And again, here, we get basically the same results that we had up here, but it all does it in one step. And so you can kind of split it in this way, right? Here I have the vector z, okay? The vector z represents, you might have some kind of strata in your data, right? So you might have, maybe you have, I don't know, males and females, represented in your data. And maybe you want to make sure that when you do your train test split, both of those genders are equally represented, okay? At least, when you go through the data. And so you can say, when I stratify, I want to make sure we split x correctly according to the strata. And I also want to get, and we can do that. So here I'm going to do x train, x test, and normally you would put in the x and the y, but here just to kind of illustrate how the strata is working, okay? So here, it's going to do its best to try to make sure that both x and y are equally represented. Now, with a test size of 1/4, it's a little bit difficult to do that. If I did, let's see, test size, say 40%, it'll, it'll make sure that we get two observations from strata 1 and 2 observations from strata 0, okay, to kind of make sure that the split is appropriate. So you have kind of both strata 0s and 1s equally represented when you split the x and the y, or in our case z here. But here I can kind of just demonstrate, just leave it as z here. So if you do have some kind of strata, you can make sure that they get split according to the proportions that appear. Okay, so that's kind of an overview of how train test split will work. Okay, and here we'll just kind of explore a little example. Okay, and so here I've loaded up some data. Okay, and this is some application from manufacturing, and this is like an ancient data set, but this was back in, like, well, not back, they still do this, but when they wanted to kind of see if test the in kind of metal when they're forging metals and kind of purifying them, there's a few different ways to kind of test how pure the iron is and things like that. Okay, and so there is a magnetic test and there's a chemical test. The magnetic test is cheaper, the chemical test is more accurate. And the question is, can we use the magnetic test to predict the chemical test result? Okay, and so so this CSV is included. I've put that on the GitHub, and you can kind of download that. And so I'll just read that in using pandas read_CSV. Okay, and so this is just kind of the head of the data set. All right, And this data set, there's a total of 53 observations, and we can see that there's 2 columns here, right? And what we're going to do is we're going to try to fit some kind of model to see, to predict the chemical score based on the magnetic score. Okay, and we're going to just try out a whole bunch of different things. And I'm going to illustrate the ideas of cross-validation here. Okay, let me go ahead and give you your first view quiz answer for today. Today's view quiz answer is the letter E. E as an elephant. E as an elephant will be your first view quiz answer. Okay, so just so you can see the full data set, this is what the full data set looks like. And I'm going to go ahead and I'm going to create a train test split, okay? And so we're going to kind of create some kind of holdout set. All right, and so I'm going to do train test, and we're going to take just the full data set here, iron. And so train test split allows for, it can take in NumPy matrices or NumPy arrays. It could also take in pandas data frames. So here iron is a pandas data frame, but we're going to do train test split, and I'm going to just say 1/5 of the data will go into a test case here. Okay. And so if I do that, these will be the observations that go into the training set. These will be the observations that go into the test set, and that's fine. Okay. And so here's a plot. Let me, so this is the full data set, and here is the training data. Maybe I'll just kind of copy this one more time here, just so you can kind of see, just so you can kind of compare. So there's a few, just basically 1/10 of the observations, and you can see some of the observations, right? Like this observation. So only a handful, right? So there's maybe 1/5 of the data out of here is missing, okay? And so this is what we're going to be using to train our data. Okay, so we're just going to use the training data, right? And what we're going to do is we're going to try out some different possible models, and we're going to use cross-validation to help us evaluate which model is going to be best. Because, you know, again, without cross-validation and without kind of our classical statistical tools, how can we evaluate models? We don't have your likelihood ratio test. We don't have ANOVA and things like that. At least not in this perspective, because we're taking kind of the machine learning approach rather than the classical statistics approach. So we're going to use cross-validation. All right, and so so this is what we're going to do. We're going to take the values in the magnetic, okay, and I'm going to turn it into an X matrix. All right, and here I'm going to take the values in the chemical column, and that's going to be kind of my Y array, right? So we're going to take, so when we did our train test split with 53 observations, you know, we end up with 4,200 training set, okay? And just so you can kind of see what we get, you know, right now our correlation coefficient between X and Y, you know, kind of the linear correlation, Pearson correlation is around 0.708. And so if we were to fit a model using that, we would get an R-squared value of around 0.502. Okay. And so, you know, just to show you, if I fit a linear regression on the full X data, right? So X is these 42 observations on the Y. So my full kind of training data, all of the X and all of the Y, okay? It says, you know, the score you get, which is basically the R-squared value, is 0.5023, right? So this is basically your R-squared value from linear regression, right? And we can kind of just see, you know, this is basically the fitted line on the full data set. And the question is there a better model that we can use? You know, will a quadratic model, a cubic model, you know, 4th order, 5th order polynomial, will that be better? Is it better if I transform log X into a log value or something like that? You know, is something like that going to perform better? Okay, so so we're going to just try out a handful of these models, and we're going to use cross-validation as our guide. Okay. And so as far as cross-validation goes, there is a tool called shuffle split. Okay, so shuffle split, and you say n split equals 5, will kind of split the data into 5 equal parts. And I forget, I'm sorry, test size 0.3. Maybe I should, well, and so this will kind of be our cross-validation sets, all right? And then we can use, we can get a score, a cross-validation score, using this, this function, cross-val score, using the model, the linear regression model that we just fit here, okay, where we fit X and Y, okay? We're gonna compare it to our X and our Y data using the cross-validation splits that have been created by shuffle split here, okay? And if we run this, it tells me my cross-validation score is about 0.471, okay? This is my cross-validation score, 0.471. That is, you know, it's lower than our correlation coefficient, but that's expected, okay? So this is our score, and this number 0.471 is going to be the mean of these values, CV underscore linear. When you do a cross-validation score, you know, we have 5 splits, it's gonna give me 5 values, right? And we can see, you know, some of these things we get higher scores, 0.58, 0.53, 0.45. This one came out pretty low, 0.1369, and this one came out pretty high, 0.653, right? So where are these numbers coming from, okay, when we do cross-validation? All right, and so what I wanted to try to show you was where these cross-validation scores come from in the first place, and what it is that you're getting when you use scikit-learn's cross-validation score, because this is often the tool that we're going to use when evaluating models, when comparing one potential model with another potential model, okay? So technically this is all you need to do, but I've written a huge code chunk here that's going to kind of illustrate the plots, illustrating how all of this stuff works, okay? Now, I guess maybe for maybe a quick review of linear regression, and so when we talk about mean squared error and mean squared regression, you know, I kind of want to make sure that we understand what we're talking about here, right? So let's say you have some data like this, okay? And so your mean squared error would be kind of just, if you take the mean, okay, if you just take the mean in the mean value of these blue dots, you know, how much variance do we have? Where's the mean? Okay, maybe somewhere around here, okay? And so basically you're going to kind of be measuring the length from each dot to the line, right? You're going to kind of square all these things, and the average squared distance from the mean, this is going to be kind of your mean squared error, right? And then mean squared error is going to be basically equal to the variance, and it's going to be each observation minus the mean squared summed up over n minus 1, okay? And then over here, your mean squared regression, and you got your kind of your line of fit, okay? And now you're going to take, I'll use a different color here. You want to see, okay, how much difference is there between each dot and the fitted line? well, actually, this is kind of the leftover here, right? Sorry, this is not the mean squared. These are not the right terms that I'm using here. But okay, but this is kind of your total variation. Here we look at this, and then the reduction. There's a kind of a reduction, and this is basically what your R² value comes down to, is how much did our predictions change and improve versus the total variance. Okay, so each dot now, you know, we've got some kind of quantity going from the line to each thing here, to there, from there. So we're improving, or our amount of prediction error is changing by this amount here, right? So your mean squared, your mean squared regressions will kind of be the difference between each of your test observations, your y, minus your y hats. You're going to take that difference, okay, and you're going to kind of sum those up and square those, and you're going to divide by n-1 here, okay, or maybe n, and then the reduction is kind of how much basically your mean squared error minus your mean squared regression divided by kind of the total mean squared error here, or the total variance, right? How much of your variance was reduced. And so if you have very good, if you get some kind of data set where it fits it perfectly, okay, then these quantities will be huge, right? So your reduction is going to be huge, okay? Whereas the original values will be a little bit different. So, all right, so let me just kind of run through this here. All right, so what we're going to do is I'm going to go ahead and go through all of the cross-validation splits here, and we're going to fit a linear regression model to all of these things, and we can kind of see how this ends up going, right? So what the cross-validation split is doing is it takes your entire training data and it splits it, right, into kind of 5 different chunks here, right? And so this represents 4 out of the 5 chunks of data. So we had 42 observations, and we're going to see, okay, how far off, what is the best fitting line that we can have for these observations, okay? And then the remaining observations, we're going to see how good is the fit here, okay? So we say, all right, how far off are predictions from here? How far off are predictions from here? And we say, how much of a reduction do we get? And we actually got fairly decent reduction, and we have a score of 0.581, right? So this is how much improvement do we have using the red line to predict the green dots versus just predicting the average, right? So the baseline is just predicting the average for everything, right? So using kind of, this is the test case. If you didn't have any data, you would just predict the average for everyone. All right, so let me just kind of compare this where we have a decent score versus, you know, an example where the score ended up quite poor, right? So this score ended up 0.1369, okay? And basically this is our training data of when we did cross-validation, okay? So this is represents 4 out of kind of the 5 sets. And we said, you know, what's the best fitting line here for this data, all right? And so this is the red line that we fit, okay? And here is the test cases, okay? The test cases is this kind of cloud of green dots. And so with this cloud of green dots, we ask, do we get better performance by using a red line versus just predicting the average? Okay, and the answer is the improvement is very little, right? So if we said, you know, how much how much do we reduce kind of the overall error, right? So the overall error here is we're going to kind of predict the overall kind of variance of these green dots is, compared to the mean, which is this flat line, how much improvement do we get? There's not that much improvement, okay? Compare that with something over here where the green dots in the test case line up quite well. There's quite a bit of improvement by using the red line over just a flat green line, right? And so depending on kind of the training and the test split, the kind of the cross-validation split, I should say, the training and the validation split, we get different scores, okay? And then so we have a total of 5 of these things, and the average of all 5 is going to be 0.471. Let me compare that, say, to using a quadratic thing, okay? Because when we do it with a quadratic model, okay, by using a quadratic model, our R-squared values go up a little bit, okay? Using just a linear regression model, our R-squared value was 0.502, and the cross-validation was 0.471. Using a quadratic model, instead of 0.502, we're up at 0.509. So our overall R-squared on the full data set has gone up, okay? And so this is kind of the overall fit on the full data set. But then if I use cross-validation, my cross-validation score dramatically decreases to 0.2623, all right? And so this cross-validation score, even though when looking at the full data set and using a quadratic model, improves my R-squared, the cross-validation says, you know what, the quadratic model is probably not the best fit, okay? Because the idea here is anytime you make your model more complicated, your R-squared value is going to keep going up, right? Anytime you add extra variables or extra terms, you can generally improve your R-squared. But is that a true improvement? And the answer is not really, because when we look at the cross-validation score actually goes down. So when you compared R-squared onlys, it went from like 0.502 to 0.509. When you go for cross-validation, it went from something like 0.471 down to 0.2627, 0.263. So what's happening, okay? So here, again, I kind of create a plot of showing this. And again, what we have is we've got some training data, and we've got some, and based on the training data, this is the quadratic line that we're going to fit to these data. And then we're going to use that same fit to the test data that we haven't, the validation data that we haven't seen, that wasn't used as far as training this goes, okay? So, when you see all of the data, it's easy to kind of fit the correct quadratic line, okay? But when you're limited to only a part of it, okay, which is kind of what we're trying to simulate is, we only have part of the data in our training data, and we want to make sure that this is going to generalize to the full population. When we do this, we can see, you know what, the quadratic line has this curve, and if I add this observation back here, it doesn't really do a good job, okay? And so, so here my score, how much improvement do I get using the red line versus using just the green line, using the median? This is, if I just predict the mean for everybody, the mean for everyone, I would get some kind of mean squared error, the variance. And by using the red line, how much improvement do I get? Not that much, okay? My reduction is about 20%. And you can see it actually, in one of these cases, it actually performs worse, okay? So here, it's the line is trained on these purple dots here, okay? It's trained on these purple dots. And so this is the fitted red line that we get. And what we're going to do is we're going to say, okay, well, let's use that to predict these green dots, okay? And in this case, we're actually getting worse performance, okay? Because if you look at the flat green line, there's not much error for this data, right? This dot is pretty close to the flat line. This dot's pretty close to a lot of these things. there's actually more, comparing this dot to kind of what the red line predicts, there's actually more, more error here. And so what this is saying is that your performance for prediction actually goes down, okay? Or actually the difference between the red line and the green dots is actually greater than the difference between the green line and the flat green line, okay? The green dots and the flat green line. And so in this case, our score actually goes down. And so because we're getting kind of some of these negative values, the overall average ends up quite low at around 0.263. Okay, in some cases it does well, right? So like in this test case, using the red line as a prediction, we're actually reducing the amount of error in our test case quite a bit, okay? But in other cases we're not. Let me go ahead and give you your next view quiz answer. Next view quiz answer today is C as in cat, C as in cat, okay? And so this just gets more and more extreme as you make your models more complicated. So I'm going to go ahead and fit a cubic fit, all right? And so to fit higher order polynomials and things, we're using a pre-processing feature. This is what we use in scikit-learn to kind of expand, you know, to take, you know, some variables x and then turn them into, say, cubic, quadratic, or cubic, or fourth order polynomials, right? So you use a pre-processing thing. You're going to kind of take this thing, which I'm calling polynomial 3, poly3, and then you use the command fit transform. So you're going to transform our input x matrix, okay, to transform that, and then we're going to fit a linear regression model between the transformed x and the y. All right, and so here my r squared value continues to get better, 0.514, all right? But again, using cross-validation, we see that it's overall, it's not going to perform better, right? So this is, when you have the full data or the full training data, we actually still have a holdout set. This is kind of the fit that we see, but is it actually better? Our cross-validation score is quite negative, negative 0.314, right? And so just to kind of show you what's happening, here, this is the cubic model that gets fit to this data, right? So again, with high order polynomials, you can get kind of these interesting shapes. And so, you know, according to the data that we've seen, this is the fit that we get. And then when we include kind of our validation set, we say, oh, you know what, this is actually doing a bad job, right? We can see this was part of our validation set to see, oh, how well did we predict? We're doing a poor job predicting this green dot here, okay? Versus, you know, when you have the full data set, it's going to try to fit that. But when you only see part of the data set, which is basically the situation that we have, except the full data set's the whole population, when we simulate the idea of, you know, kind of looking at only a part and fitting a model on that just portion and generalizing to data that we haven't seen, we can see it performs poorly, right? And so here it even gets worse, right? So on this is our training data here, okay? And based on this, you know, as far as the data that we've seen, the red line tries to do its best on the data that it sees, okay? And because it's a cubic model, it just starts to veer off, you know, a little bit wildly, okay? And so it veers off in this way. And so if we compare this line that it fit onto the training test data or the validation data, we can see, all right, does it do a better job for the green dots? Okay, you know, for these dots, it actually does a better job than predicting a flat line, okay? But with this observation, this does a really bad job, right? And again, when you're looking at squared errors, big distances are punished very, very harshly, right? And so here we're splitting the difference between our prediction out here and the true value is really huge. And so we're actually performing a lot worse using the cubic line than if we just predicted the mean for everybody. If we just predicted the mean for everybody, we would have less squared error. We would only have 23.56 versus if we use the regression line to make predictions, you know, our squared error here is around 42. So this is a lot worse. And so we're like 80% worse here. Okay, question, how many different training sets are there in this cross-validation? So for the cross-validation here, I think we did 5. And we said, you know, split between, you're going to have basically 5 different kind of validation sets here. Okay. And so, so here we're doing a lot worse. Here we're only doing marginally better. Okay. Here we're doing a little bit worse, and in this case we're doing worse again. All right. And so in all of these cases, the kind of the commonality is that this observation, the cubic model gets, you know, takes kind of this U-turn and starts pointing down, which is the wrong direction. Okay. And so kind of what we're trying to say is that, you know, if you were to generalize this to the population fitting a cubic model on only a portion of, you know, on the data that we've seen, you know, if maybe it looks pretty good here, but then when you generalize to the entire population and there's observations you haven't seen, it might perform poorly, right? And it just gets more extreme as we go into kind of with a 4th order polynomials, we get 0.08, and in 5th order polynomials, it actually we get -78. Okay, and again with a 5th order polynomial, you know, for the training data, it will fit well. Okay, and but when you look at your test cases, this is the example. You know, when you fit 5th order polynomial, it fits this data really well, but you know, when you got an x to the 5 term, it can take huge, you know, really sharp turns and stuff. And so here it takes a really sharp turn because, you know, it's just trying to fit data on, it's just trying to fit the data it sees, and it doesn't actually know how to extrapolate beyond that. And so it does really bad. And so using how much error is there between the red line and the green dots, there's a huge amount of error, versus if we just use the mean for everybody, we would have gotten a lot better performance. Okay, so we're getting all kinds of our performance for the degree 5 polynomial is bad. Okay, all right, so anyway, you normally wouldn't be plotting all of these things. You would just kind of do cross-validation here, and you would just kind of fit a linear model. You'd set up your cross-validation splits, and then you would ask for the cross-validation score based on your cross-validation splits. Okay, and so here we would do our, you know, our cross-validation score is 0.471 for the linear model. Okay, for the quadratic model, you say, all right, what I'm going to do for the quadratic model is I'm going to transform my x values into a quadratic form using pre-processing polynomial features. And then you fit a quadratic model by just using linear regression, but using the quadratic x to make your predictions. So you do that, and then you ask for the cross-validation score between the quadratic model and the quadratic x. And when you do that, again, your cross-validation score, you know, drops down to around 26%, 0.26 versus 0.47. We can try it for the cubic model, and we get a cross-validation score, and it actually gets even worse at -0.314, right? So all of these things, 0.47, 0.26, and -0.34. And it seems strange getting -0.34 because this is kind of the equivalent of an r-squared value, right? Can your r-squared value ever be negative? And the answer is, yeah, it can actually be negative when you talk about how much of a reduction is there between just the you know, sum of squares between x and the mean versus x and the predicted line. If your predicted line actually does a worse job than using the mean, your r-squared value is actually going to be negative, and that's what we're seeing here. Okay, I didn't create graphs for like a cross-validation thing with a log transform, but you can take x and you can transform it, and you would use something like a function transformer. So the other things that we've been doing is we've been transforming using polynomial features, but there's other transformations that you can apply. And so here I'm going to do a log transformation. So we're going to do a function transformer we're going to apply the NumPy log function onto to transform our x values. Okay, and so that's going to create log x. We're going to fit a linear regression model between log x and y. And we get that. And we can ask for the cross-validation score. And we get this. You know what? Yeah. Okay. And so this is a little bit lower, 0.378. So between all of these models, it seems just like the plain linear regression model actually performs the best. Okay, using cross-validation as a way for evaluation. It's and so anyway, this is kind of how we would go about evaluating models using cross-validation. And so what we'll do on Wednesday is we'll use some of sklearn's features using cross-validation, because there's kind of automated forms to try out a bunch of different kind of model parameters. Should you fit? So here we tried out a bunch of linear regression models. Should I fit just a linear model? Should I fit a quadratic linear regression model? Should I fit a cubic linear regression model? And it turns out that just the linear model is the best. But in Wednesday's lecture, we'll try it out. But we can say, what, let's try a k nearest neighbors classifier, and what size k should I use? Should I use k equal 1, 2, 3, 4, 5? And there's kind of an automated search feature that can help you by using cross-validation to kind of help you figure out what's the best parameters to use here. Okay. We'll just call it a day here. Let me give you your last view quiz answer. Today's last view quiz answer is the letter A. A as an apple. A as an apple. Okay. If you go through the code that I've used, I've used a whole bunch of things. The primary things that I would recommend you read up as far as documentation goes will be Traintestsplit and cross-validation score. Read through the documentation there. There's some examples, and that should help you, at least guide you as far as, how can you evaluate your model performance against different potential models if you want to compare models. Okay, we'll call it a day here, and we'll see you guys on Wednesday. Have a good evening.